الرحمن الرحيم. My name is مدرس حامد حسين هدوان, University of Babylon, College of Engineering, المسير, Department of Automobile Engineering and Department of Energy Engineering. Our lecture today is entitled of Classification and Characteristics of Instruments Part 1. اجهزة القياس وأنظمة السيطرة. Measuring Engineering System في الأنظمة الهندسية. Behavioral objectives. After completing this lecture, the student should be able to, first of all, list the classification of instrument, illustrate the characteristics of instruments, discuss advantages and disadvantages of measurements. Introduction. Measurements are the basic means of acquiring knowledge about the parameters and variables involved in the operation of physical systems. Measurement generally involves using an instrument as a physical means of determining a quantity or variable. An instrument or a measuring instrument is therefore defined as a device for determining the value or magnitude of a quantity or variable. Outline this classification. After that, gauge and non-gauge measurement system, active and not active devices. It's called passive, like analog devices. Null type, like scale, deflection type. It's opposite of null type, indicating signal output. Manual and automatic, like pressure devices. Smart and non-smart devices. Contact and contactless devices, analog and digital devices, and finally absolute or primary devices, and secondary instruments. First of these instruments, gauge and non-gauge measurement system. Gauge like this in this picture to illustrate a very simple measuring system. Let us consider the familiar tire gauge used for checking automobile tire pressure. Such a device is shown in the figure below. It consists of a cylinder and piston, a spring resisting the piston movement, and a system with scale divisions. As the air pressure bears against the piston, the resulting force compresses the spring until the spring and air forces balance. The calibrated system stem switch remains in place after the spring returns. The piston indicates the applied pressure. And second type of these instruments, active like digital devices and passive like analog devices. Passive sensors do not add energy as part of the measurement process, but may remove energy in their operation. In other words, energy is converted to measurable quantity. One example of a passive sensor is a thermocouple, which converts a physical temperature into a voltage signal. Active sensor add energy to the measurement environment as part of the measurement process. An example of an active sensor is a radar or sonar, where actively sended radio, radar, or acoustic sonar waves reflects of the some object and thus measures its range from the sensor. And third type of these devices, null type, and the opposite type, deflection type. Null type like scale, null measurement, null instrument, measuring devices that balances the measurement against a known value, thus achieving a null condition. Two inputs are essential to the null instrument. Null measurement devices usually consist of, first, automatic or manual feedback system that allows the comparison of known standard value, and second, an iterative balancing operation using some type of comparator and third, and a null deflection at a parity. And null type, like scale deflection type, the advantages minimizes measurement loading errors. In other words, alter the value of the measurement signal effective when the measurement or the measured value is a very small value, minimizes interaction between the measuring system and the measurement by balancing the unknown input against unknown standard input. Achieving perfect parity zero condition is limited only by the state of the art of the circuit or scheme being employed. Disadvantages: slow and iterative balancing operation requires more time to execute than simply measuring sensor input, not suitable for fast measurements, i.e. only for static measurement. Example, an equal arm balance scale with manual balance feedback and second potential meter اللي هي المقاومة المتغيرة. The potentiometer AB is the potentiometer wire with resistance R1. The EMF electromagnetic force of a standard DC source is E volts. The rheostat resistance is R. If the null point is obtained at point C, then the electromagnetic force of potential and E1 are equal. Deflection instrument measuring devices whose output deflects devices proportional to the magnitude of the measurement. Advantages: high dynamic response. In other words, can be used for fast measurements, can be designed for either static or dynamic measurements, or like in this picture. And null type deflection is instrument disadvantages by deriving its energy from the measurement. The acts of the measurements will influence the measurement and change the value of the variable being measured. This change is called a loading error. Example, sibling scale as a deflection instrument. Scale has to be calibrated. Four types of devices for instruments: indicating and signal output. Indicating instruments are those which indicate the value of a quantity that is being measured at the time at which it is measured. Such instruments consist essentially of a pointer that moves over a calibrated scale which is attached to a moving system pivoted in a bearing. The moving system is subjected to the following three torques. First, a deflection or operating torque, a controlling or restoring torque, and a damping torque. Indicating signal output, the deflection torque is produced by making one of the magnetic, heating, chemical, electrostatic, and electromagnetic induction effect of the current or voltage and cause the moving system of the instrument to move from its zero position. The method of producing this torque depends upon the type of instrument. And fourth type, indicating a controlling torque is obtained. This weight is called the control weight. Another adjustable weight is also attached to the moving system for zero adjustment and balancing purpose. This weight is called balance weight. To overcome this difficulty, a damping torque is to be developed by using a damping devices attached to the moving system. The damping torque is proportional to the speed of rotating of the moving system. That is T variable equal kV d theta by dt, where kV damping torque constant and d theta by dt speed of rotation of the moving system. Under damping condition, the response is oscillatory. Over damping condition, the response is sluggish, and it rises very slow from S0 position to final position. Critically damped condition, when the response settling quickly without any oscillating is produced by the damping torque is produced by the following methods: air friction damping, and second fluid friction damping, and third eddy current damping, and fourth electromagnetic damping. And this state in this picture, final deflection for the in the y-axis, and in the x-axis the time, and depend on this response we have under damped is oscillate over the normal damped, and over damped is like slow down and sluggish below the normal damped, and critically damped it's exactly came and like stable, become stable directly without any over damped or overshoot of the normal response of the final value. Thanks for attention. Any question you can text me. Finish.